Okay, thank you. When I was asked to do this a year ago, I probably should have thought more about it being December, the hardest time of the year, but I'm super honored to be here and asked myself the question, why did I get invited for this? I've never considered myself a creative person. Growing up, I could never draw. My piano teacher called my parents and told them that they were wasting their money on me, which is honest. And I'm glad she did, because I have zero musical skills. I loved Legos, but I never really built creative things out of Legos. I just loved following the directions. My wife, on the other hand, she drew this at a cheap Mexican restaurant with a margarita in October, and I was just like, how do you do that? How do you sit down and draw this? So I wanted to start this off lightly because it's been a long time since I've done one of these decks in a corporate environment or just in front of people. So so please forgive me if I stumble or pause or go over the time limit, but I've got a timer here, so hopefully that doesn't happen. So I wanted to talk about innovation in the context of, or as it relates to creativity. And I think really innovation is just creativity applied in ways that impact people on the planet. That's sort of where the title of the deck came from. But I think it's also important to note that it's positively impact. What's different about innovation is it really, really requires collaboration and perseverance. I know that was discussed in the intro. And compromise, there's always a lot of compromise when you're innovating. And I wanted to mention that none of these projects that I'm going to talk about today were just me. I mean, it's a team of engineers and so many people involved in all of this stuff. I do think innovation's a bit overused, and even my own company is called Adherent Innovations. When I named it, I probably, 15 years ago didn't realize what innovation meant, but I have my own different definition now, and we're going to get to that. So where did this begin? Like I said, I liked Legos as a kid, but I just kind of followed directions. But in the 80s and 90s, these really cool bikes started showing up, these carbon fiber frames that looked very different from traditional welded steel frames. And sailboats started to look less like these old wooden ships and more like airplanes. I mean, this is a solid wing sail on a trimaran. So I remember seeing these things like, man, how do they make this stuff? Why does it look that way? And got really interested in materials and design and manufacturing. The Y bike, I remember opening my dad's bicycling magazine and seeing this thing that is so cool. So fast forward, I think it was, 10 years later, I graduated college as a mechanical engineer with the goal of working at a company like Trek or Mega Yachts in Italy, these really cool 100-foot carbon fiber boats. But all of the innovation in composites, carbon fiber, and materials and manufacturing was actually happening in Seattle, in my hometown. Grew up on Bainbridge, but Seattle, close to home. And it was happening in aerospace. And it was really happening in aerospace because this is where the constraints and compromise of weight, strength, stiffness, drag, all of these competing variables are happening when you're designing an aircraft. And the 787 was the first primarily carbon fiber based aircraft. Airplanes up until then were mostly aluminum. There still is a lot of aluminum on the 87, but it's carbon fiber, and mostly in the fuselage and wings. And what this does is it lowers the weight of the aircraft, which improves fuel efficiency, which is the #1 operating cost for airlines, and obviously the biggest influence on our planet. There's some other benefits, like the wings are super flexible. So if you've ever flown on a 787, it's really comfortable through turbulence, and you can actually watch when you take off and land, the amount of fuel burn. The wings, when you land, are actually, most of the fuel stored in the wings, when you land, the wingtips are like above the fuselage because all that fuel is gone, which was what was keeping them down. It's a pretty crazy airplane, really, really fun project to work on. The carbon fiber also enables higher cabin humidity and pressures, so you feel a little bit better after that long haul flight. And I'm super grateful to have had the opportunity to work on that when I did. This is a slide that will deter any student from going into structural engineering. But when you're designing aircraft, the whole goal is to minimize weight. The way you do that is by focusing on a parameter called stress. And stress is the amount of force over a given cross-sectional area of material. You can kind of think of it as like pressure. It's in the same units, pounds per square inch. And every structure out there can kind of be simplified to these different shapes and then these different load cases. And all of those equations were used historically to design things like aircraft and bridges. And we used a lot of this at Boeing. But fortunately, we also have computers now. And I was at Boeing at a time when we were transitioning from primarily that classical stress analysis method to what is now called, or what is called a finite element analysis method. And what we do is we basically use CAD, the computer-aided design of our structures or of our products, and we can apply material properties at a very, very fine level. And this is critical for composites. So what's unique about carbon fiber versus aluminum or steel is it's an anisotropic material. The properties are different in all directions. So in the direction of the fibers, carbon is very stiff, very strong. Transverse, you're really just stressing the glue that holds it together. So composite structures are comprised of these layups with the fibers running in all different directions. And there's really no way to do this structural analysis with classical methods. So we do it on a computer and we apply the mechanical properties. And we can look at things like how much does the wing bend, when it encounters an emergency landing or turbulence. In automotive, it's massive for crash worthiness because all of this testing is crazy expensive. You can't just build an airplane and crash it and see what happens, or run a car into a wall and hope that it works. Just the tools to stamp the body panels and the A pillar and the B pillar, all of that stuff takes years. And so by doing this on a computer and using finite element analysis methods, we can learn and innovate crazy, crazy fast. And I can do this analysis now like on a laptop. I mean, Boeing, 30 years ago, you needed a mainframe and it was crazy. And now we can literally do it on a computer. So my time at Boeing, just to wrap up that kind of phase of my career, as I said, it was a really wonderful place to start a career. And it was fascinating for me to really, sorry, I'm missing this. I'm still amazed that airplanes fly. I mean, as an engineer who's worked on them, it's insane. And I took this picture. This is actually my photo that I took at 787 first flight. And as much as I wanted to be in the crowd, I wanted to get away from the crowd and show them in the photo because it's all these people that made this happen. And for me, seeing the economic impact of manufacturing, I remember being in Italy with one of our vendors at a pizzeria in this tiny town and thinking I'm eating this €2 pizza in the middle of nowhere, all because we're building that. And it was so powerful. And the biggest thing about Boeing is it's where I started my career and really gave me that urge to innovate and work on these other crazy projects. So shortly after delivery, I kind of indirectly went to Apple. I went to this flying car startup that I'm not going to talk about in this meeting, but that was crazy. So at Apple, I went from, in the aerospace world, I was an analyst, we were responsible for, sizing structures. At Apple, I was a product design engineer. And so it was the first time in my career that I had that imposter syndrome thing. I was like, whoa, what am I doing? I'm like a total, analyst, math geek at a firm with people who dress really well and design amazing products. But really, Apple was insane, the level of compromise that goes into making these products. I mean, it's just like designing an airplane. I mean, instead of maybe weight and aerodynamic drag, you're looking at like, how do we make 1 billion of them in a year or something? How do we make it look really good? So it was really, really cool to see the level of compromise and constraints in such a different way at Apple. It was a wonderful place to work. Sometimes I do regret leaving when I'm like in the depths of customer service emails or printing shipping labels, for my own business. But it was a wonderful place. And what I did there was I managed kind of a simulation team, and we were focused on improving the reliability of our products. So this is an example of finite element analysis being used to predict the stresses in the corner of a phone when it's dropped without a case and then with a case. And it's hard to see the axes in these graphs, but what this is showing is the accelerations result in forces over areas, your stress. So this phone with the case has a much lower peak stress than the one without the case. I think that one goes to, 1600, and this one's 8. So you can see the color, a lot more red, a lot higher stress in this one, a lot lower over here. So just with a case and without a case is one example. You can affect the stresses by changing the material, changing the design. So we would use these tools to work on these products and improve reliability for cases like drop specifically. So I was one of the lead analysts or designers on the 13-inch iPad Pro. So this was back in like 2013, 14 era. It's hard to believe it's been that long. But yeah, this really big iPad was basically cracking every time it was dropped. So we build like 1,000 iPads and we'll drop them with a high-speed camera and correlate that data with analysis methods, with the finite element analysis methods. And it was failing like every time. Basically, the whole thing was folding in half. And at the corner of the iPad Pro, at every corner, there's a speaker. And the speaker is like this injection molded plastic box with a driver, the audio driver, the same kind of driver that's like in your headphones. But then there's a bigger acoustic volume. And I noticed that the speakers are really big on the Pro because there was a lot of room. And I was like, what could we do to improve the stiffness and strength of the enclosure? These plastic speakers aren't really doing anything for us. So I looked at a concept where we actually machine that plastic box so this aluminum enclosure is actually machined out of a billet of aluminum. So it's a CNC machine. You put this brick of aluminum inside, and this tool comes down, and it literally machines the iPad out of one chunk of metal. So we were just machining all that material away. It was gone. But if we had that material there, why not use it? It's much stronger than plastic. It's free. We're getting rid of it. So I looked at this concept where we actually machine the acoustic volume out of the aluminum, and then we put this carbon fiber cap on top to seal it, and that becomes the acoustic volume. And then the speaker driver is just this little guy right here. And we went from basically a 0% pass rate to 100% pass rate on drop, which was super, super, super cool. And then there was also like amazing, yeah, we've all dropped our phones and iPads, I know. Really good acoustic benefits as well. I mean, when Sir Johnny Ivy launched this product, I remember him saying like, this iPad has the same acoustic performance as our 27-inch iMac Pro or iMac, and I was like, man, that is so cool to hear him say that. So that was a really, really, really fun project. And working with the ID team, industrial design team, they're like the top of the totem pole at Apple. Like us product design engineers basically had to do whatever they said. And it was make it thinner, make it smaller, make it stronger. I actually found that the performance was even better if we orient the fibers in a plus minus 45 degree in the corner of the iPad. But the ID team didn't want to see that when the customer, if the service or customer were open, they engineered the inside of the product to be beautiful. And they wanted the fibers running along the orientation, the primary axes of the device. So even though it was better performance, it was like, nope, we want the fibers running this way. So it was wild working with them. About 3 years into Apple, I had lunch with a buddy from Port Townsend. He was working with this company called Atlas, and they were making these massive vacuum chambers that were used by these flower growers in Bolivia and Colombia to store roses and flowers. And the problem is if those flowers ripen before Mother's Day or Valentine's Day, like you lose like 50% of your revenue for the year. So these vacuum chambers were being used to hold those flowers to market. And they wanted to develop a smaller chamber that could be shipped and transported for fruit and other perishables. And my buddy asked me if he thought we could do it out of carbon fiber or plastic. I was like, that's kind of crazy, but I think we could do it. So we did some trials with like lab grade vacuums, obviously not transportable. They were outfitted in a Sprinter van. We held citrus. This is a trial with fresh cut mango. So we actually cut mango, put it in the vacuum for a month, and it was edible. It wasn't very good, but that's not in the vacuum. So to do the plastic version, I took an off-the-shelf roto-molded bin, put a bunch of structure in it, we pulled vacuum on it, and it actually held. 15 PSI doesn't sound like much, but when you have that much surface area, it's like 15 to 20,000 pounds of force. You can't see it, but that's how much pressure is, or how much force is pushing on that. There's a lot of constraints. We're trying to, make a product that we can move around the logistics chain, keep the costs down, allow people to put stuff in, take it out. And I went to this trade show in Germany called K-Fair, and it's the biggest plastics trade show like in the world. Everything you can imagine that's made out of plastic, from chairs like this to plastic bags. And I walked by this booth where you've probably seen, given where we live, these stormwater pipes. And I thought, what if we made the right blocker round and we could make it like this? So these are made in these massive corrugators. Each one of these is about 10 feet tall. The tooling to make it costs almost $1 million. Before we get to that, I wanted to just test it and make sure, again, that my analysis methods correlated with the results. And we ended up actually making our own molds, and we can make about 32 right blockers an hour, as opposed to the square design, which took a lot longer to make and needed all this internal structure. So this was a picture I took at the facility in Ohio that ultimately extruded these. Right blocker, man, there's no bigger industry than food. Like, it is, as far as like impactful things I've worked on, like food is massive. Right blocker, our goal was to reduce waste, lower prices. Washington has so many good examples for like economics in the food industry. I mean, cherries ripen in July, flood the market at $2 a pound, then they're gone in August. So if the farmers could hold the cherries longer and release them in August, September, it'd be massive. It was a really, really fun project. The biggest challenge with this, I felt, was actually the logistics, which is not my expertise. And I think it's something that they're still trying to figure out. This was a deployment with our product at Palm Wonderful. So we actually ate pomegranates out of that. We're kind of ending pomegranate season, but I was eating pomegranates in like March out of these chambers. So Cedrus, this is what I'm doing now. Not going to read the whole mission statement, but my goal was to make a product in the water sports industry that lasts, make it locally, and make it in a really innovative way. So foiling, what is foiling? Foiling is short for hydrofoiling. A hydrofoil consists of like your board. This could be a surfboard, a sup, a kite board, lots of different boards. It consists of the actual lifting hydrofoil, so the tail and the hydrofoil are connected with the fuselage. And then this thing called the mast is what actually connects your board to the foil and lifts you out of the water. So we just make the mast. We make a really innovative mast. So what's innovative about it is you can make it in any length with one set of tools or molds. And when you're making a product, you typically have a tool or a mold, and those things are really expensive, especially if you make it in the US. I mean, a mold like this in China would be about $1,000. In the US, it's 10. So I can't have a mold for every model of my product. I need to figure out a way to make it out of one. So this is a really unique way to make it. The architecture of the product is very unique. A lot of carbon masks are solid. Ours is hollow, and then the leading and trailing edge are rubber. So if you fall and it hits you, it doesn't cut your wetsuit or your leg. And then the biggest unique feature of our mast is that it's universal. So the bottom of the mast has the ability to accept these machined adapters that bolt in. There's like 40 different foil brands out there, and they all have their own mast and fuselage combo. So our mast allows you to use all of them. And those adapters are machined right here in Kingston, Poulsbo area. What else are we doing? Paint. Paint is nasty. Like when you buy high performance 2-part polyurethane paint, half of what you buy is evaporating. And for reference, a 2 to 3 gallon kit of high performance polyurethane paint is around $500 right now. So that'll last us a few months. So paint's expensive, it's toxic, it is, most of it evaporates and only a thin film remains on your product. So we're using a super cool UV curable product. It's 100% solids. Every molecule that you spray turns hard and there's no evaporative, VOCs. And developing this was really well. We're the only brand that does this. Super, super crazy R&D project. What else are we doing? Robots. Everyone loves robots. So we just launched this new mask that is manufactured out of aluminum instead of carbon fiber. So carbon, super labor intensive. You have to paint it. I really wanted to get away from paint. So these new aluminum masks are robotically laser welded. And this is also happening in Poulsbo, Kingston area. And then we're also sanding them with a robot. Sanding is really hard work. I do it, my technicians do it. It's repetitive, you're breathing dust. So these are the perfect applications for robots and AI and all those buzzwords that people love to talk about. I also want to mention economic innovation. This is my team last summer. And yeah, these jobs are really, really good for the community. I think there's something about manufacturing that's really important, how it spreads. I talk a little bit about spreading the wealth, and manufacturing jobs do that. Like my supply chain, my UPS driver, I give him a 6-pack of beer on Fridays. I mean, it is just such a good thing for the community. And a lot of us, we don't want to sit behind a desk all day. We want to be working with our hands. It's also really good for the planet. We manufacture in a place with much higher environmental regulations, and we dispose of our waste properly. And I've been to China, I've seen it all, and despite what maybe city councils will say, making stuff locally is really, really good because we care. So in closing, yeah, my definition of innovation is the act of applying new technology in new ways to improve the health and well-being of the people and planet. And it's really, really important that we leave planet in there. I think there's a lot of innovation happening right now that is actually destroying the planet, and it's also not distributing well-being, it's actually concentrating it. I mean, I think what's happening with AI and the stock market, I mean, we're seeing these circular deals take place where money is just being more and more concentrated, and it's not really, in my opinion, the definition of innovation. And I wanted to close by saying that we, as consumers, actually have a really active role in innovation by choosing how we spend our money. And I deal with it with my customers all the time. I mean, the water sports industry is notorious for cheap overseas manufacturing, and my products are always going to be compared to those prices no matter how good they are. And I just try and tell people I wish they knew how, when they spend their money with us, how beneficial it is for the community, for the planet. And when you go buy your groceries or you buy that next thing, think about how you spend your money, because it really, really does matter. And I know a lot of us are small business owners and can relate to that, and it's especially true in manufacturing. So that's it.